Welcome to the IPE Compressor Test Bench tutorial. Today, we will be presenting details of the compressor test bench solution from IPETRONIK. In this video, we will cover the following main topics. We will begin by giving you an overall introduction to the IPE compressor test bench. Next, we will present the main applications for which the test bench has been developed. Finally, we will present a functional overview of the test bench. The IPE test bench is designed to test compressors for automotive applications. It has been designed to be very flexible in order to adapt to a variety of test applications which are compliant with VDA standards. The IPE compressor test bench allows manufacturers to easily validate their products. The system's flexibility covers different test setups and guarantees high repeatability for the comparison of prototypes and for benchmarking purposes. Pipework and overall system design supports a variety of refrigerants, including high-pressure CO2. We will now describe the flexibility of the test bench system and take you through the main areas of test applications. We will begin with RAFFER testing, which evaluates endurance and fatigue. Secondly, NVH tests compressors for noise and vibrations. And finally, COP refers to a wide range of performance and efficiency tests. With the RAFFER test, we can simulate, in only 200 hours, the overall stress profile of a compressor's entire life cycle. The RAFFER test is based on VDA standards and is a mandatory test procedure for every OEM compressor manufacturer. During the test cycle, the compressor is exposed to extreme changes in operating conditions, which are controlled by the IPE Motion Test Program, providing information on various RPM profiles, different high or low pressure ratios, extreme changes in workload and refrigerant mass flow, variations in ambient temperatures within the heater box, ranging from -30 degrees to up to 150 degrees Celsius, and different levels of superheat in the range of 5 to 45 degrees Kelvin. During the NHV test, the noise and vibration impacts of the compressor are analyzed. One part of this test measures gas pressure and gas pulsation at the low-pressure intake and high-pressure outlet sections. It also looks at gas pulsation-caused negative impacts on the compressor and the HVAC circuit. In the image on the screen, you can see the application of a gas pulsation pressure transmitter. Other important analysis components include compressor vibrations, taken from 3 axial accelerometers, and their frequency and amplitude of forces impacting the mounting. Together, these forces can have a significant negative impact on the HVAC pipeworks and the vehicle structure. The measurement results are presented in Campbell diagrams highlighting harmonic frequency bands with the vibration amplitudes over engine RPM at various load levels. Through this analysis, manufacturers can identify the harmonic orders causing the largest noise effects with the highest amplitudes and associated noise transfer paths. The efficiency tests put the focus on design validation of different prototypes. These tests are similar to 30-point matrix testing, measuring compressor efficiency and performance at defined mass flow, temperature, and pressure levels. The COP, coefficient of performance, is a very important test, indicating the energy balance between overall power consumption and cooling output. Another key indicator is the OCR, oil circulation ratio, which will be explained on the next slide. The oil flow inside the HVAC system is, from a technical point, absolutely necessary as it delivers the lubrication required for compressor operation. As the simulation indicates, increasing oil circulation volumes lead to oil deposits within the pipework, the heat exchanger condenser, and evaporator. Resulting oil deposits can reduce the heat exchange performance of the condenser and compressor due to isolation effects. Because of this, a vital aim of compressor manufacturers is to reduce the oil circulation flow to a minimum. Now we will present an overview of the main modules of the test bench. The centerpiece is the seismic mass with the standard VDA mounting bracket for the compressor. Mechanically driven compressors have a pulley drive from a regulated electrical motor. In this view, you see the air conditioning unit. The wind tunnel provides conditioned and flow-regulated air to the compressor box to simulate different ambient temperature situations. The cooling unit is for the air conditioning and supplies cold airflow up to -30 degrees Celsius inside the wind tunnel. The data acquisition rack is equipped with ruggedized IPETRONIK measurement modules to measure data during the test. In this graphic, we have highlighted the explosion-proof test chamber where the compressor is placed during testing. Finally, you can see the complete system. On the right-hand side, the PLC control cabinet is installed. Using the built-in PC, the operators control test cycles using the IPE motion control and data acquisition software. In conclusion, we would like to point out that this test bench is a very sophisticated system. It offers a wide range of VDA-compliant tests. The test programs are easily maintained by the IPE Motion Point and Click Data Acquisition software. And finally, it delivers very high test repeatability and reliability, enabling compressor manufacturers to compare and benchmark their products. Your questions and comments are welcome. We invite you to get in touch with us via our website or by email or telephone.